So, welcome back. We have seen the basics of CNN. Now, we will see the actual implementation using a Google Colab. Not necessarily that you should use Google Colab, even if you have an high end configuration system, if the configuration of a system is very good, you can even run this in the offline mode also. So, if you are using Google Colab, change this runtime type to T4 GPU. So, this is a good configuration to go ahead with CNN, but otherwise if you have a good configuration system, you can even work in the offline. Okay, let us start with this is an Alzheimer's disease classification problem. Here it is a 4 class problem. We have an MRI images of a brain, and then we want to classify to which what is the the level of the disease, whether it is a mild Alzheimer or whether it is in advanced stage or whether it is in an intermediate stage. So, it is this particular problem statement. From a theory class, what is that we have seen? The very first step is you have to do the data augmentation and pre-processing. What is the package that we take? Image data generator. This image data generator you will import. You will import from TensorFlow Keras pre-processing image. Then you remember in image data generator we have to specify the path. Image data generator first step is you are doing pre-processing. In pre-processing, whatever the images that is been passed, it will be scaled down between 0 and 1. Here the share range you are slanting, and then at a different scales, zoom range, at a different scale you are reading these images. Horizontal flip you have made it as a true. In this entire augmentation, there will be a very high possibility that some pixels are getting increased. You may be adding more pixel or you may be reducing. So, when you are increasing, when you require some values to those pixels, then when we add nearest is whatever is the nearest value pixel, it will add that value into a new pixel value. So, that is what is fill underscore mode. So, here first step is in image data generator, we are doing a data augmentation. Data augmentation, you are increasing more number of samples, and if you remember from the theory session, this is done only for a training, but we will not go for a testing one. In testing, we just go for a rescaling of the images. This is the first step, and the second step is you have to read the data. How are we reading the data? What is the or you have to load the data. What is the function used? Flow from directory. In a flow from directory, the very first parameter should be the path. Now, where is the path? We have given here is a train underscore directory. If you see, all the training path URL is specified to this variable train underscore dir directory. That train underscore that variable is passed here. Either you can do this or directly you can specify a path here. Next, what was the size of the images? We are not sure. Therefore, maybe all will be of same size, all will be of different, but we are scaling down everything to one particular size, which is 128 cross 128. So, we are resizing the image shape to 128 to 128. Since it is a multi-class classification problem, the class mode is defined as categorical. So, first is a train underscore data gen. In a train underscore data gen, you are passing all the pre-processing and data augmentation parameters. Then all the data that you are passing, the training data will go through that pre-processing. This is what is reading the training data, and this is what is you are making it ready for testing data also, and the path you are specifying for testing, and here also you have to specify what should be the size and what kind of how many classes, since it is an by multi-class, it is a class mode is categorical. So, the first here we are reading the data and we are loading the data and the pre-processing operation is being done. So, you can see that the number of classes here are for training, we have considered 4647 images, for testing we have considered 744 images, and the number of classes here are 4 classes. Now, we are building the CNN model. What is the CNN? How do you build a CNN model? The very first is it is one after the other, therefore, it is a sequential model. Because it is sequential model, you have to import sequential. Then what is the first operation that we do? We do a convolution operation. So, because we do a convolution operation, we have to import conv2d, and all these are convolutional layers. So, it is Keras dot layers. So, from Keras dot layers import conv2d. Next, so for this convolution we have seen 256, meaning there are 256 kernels that we are using, each kernel of size 3 cross 3. And what is the activation function? The activation function here is ReLU. What is the size of an input? Since it is an grayscale images, the number of channels here is 1. And the size of an image, because here we have reshaped the images back to 128 128, therefore the image shape is 128 128 and the number of channels here is 1. Okay. So, then once you perform this, once the convolution layer is done, then activation ReLU, we are passing the pooling. So, because we are using a pooling, we are using a max pooling, we have to import a max pooling 2D from Keras dot layers. So, max pooling, and here 2 cross 2 specifies the dimension out of 2 cross 2, that is 4, you are taking the max values. We have seen this in the example. And the second layer of convolution we are adding, that is the first set indicates convolution, ReLU and pooling. We are adding one more layer of convolution. So, here we are specifying the number of filters as 64, size of each filter is 3 cross 3. Filter and kernels are one and the same, we will be oftenly using this and we will be interchanging this, it is one and the same. ReLU. Now, when we are specifying it for the next, when we are writing for the next one, if you remember, we do not pass the same input again. The output of the previous convolution will come as an input for the next. That is the reason input underscore shape is passed only for the first, but not for the next one. I hope this is clear. So, we are again specifying, we are passing through the third convolution, and we are adding the fourth convolution, we are adding the fifth convolution. Why we have added so many convolution? Is it compulsory? It is purely a trial and error. You can keep adding more number of layers, you can keep changing the kernels, you can keep changing the number of kernels, the size of this kernel, we can. So, here this is a CNN model which is a 5-layered convolutional model. Next, once this is done, whatever is the output that we have got from this particular, from the last operation, we are going to flatten it. So, what is this flatten? Something which you have got in the matrix form, you are going to convert it into a single vector. Now, once this is done, you are now passing it is now passed to a fully connected neural network. Because it is fully connected neural network, therefore, we have used a function dense. And here there is only one, we are this indicates there is a first hidden, you are writing a first hidden layer which has 128 neurons, and the activation function that we are writing here is ReLU. And there is a second hidden layer. And the number of neurons that we are writing for that the second hidden layer is 64, and the activation function is ReLU. And between the first and second hidden layer, we are also adding the dropout. This is not a compulsory one. You can add a dropout and check how you are getting an output. You can remove dropout and you can see the performance. Next, and the last layer is your output layer. How many, this is a problem of 4 class, therefore the number of neurons that we are adding here is 4 and the activation function that we are using is softmax. So this is what is the neural network that we have built. If you see a convolutional neural network, it is a series of convolutional layers, then we are adding the flattened layer. After that it is a fully connected neural network, fully connected layers, then the last output layer. Once this is done, you are going to compile the model. So you have to, whatever the model that you have built, this entire model is CNN1 model. It's just a name that you are giving. It can be, it's just a variable name. To this model you are adding a convolution, therefore model dot add. To this model you are adding the max pooling, so model dot add. So model name here is CNN1. That's the reason you are seeing everywhere CNN1. Okay. Then you are compiling the model. For compilation you require an optimizer and you require a loss function. Because it's a multi-class classification problem, the loss function that we are using is categorical cross entropy loss. And because it's a classification problem, the metric used here is an accuracy. So once you build this model, the next is you have to train the model. What is the model name that you have trained? You have trained a CNN1. So you have built a CNN1. So CNN1 dot fit. So when you are training this model, that means you are learning each of these each of these images that are stored in your data, that are stored in your training. But when you are learning each of these data, every of this data should pass through that entire pre-processing data augmentation. So here we have specified train underscore generator. So let's go back and then see what is there in a train underscore generator. See here, train underscore generator. What is specified in train underscore generator is your training data. So how otherwise we were passing it as X train, Y train. Instead of X train, Y train, we are passing the images that are stored in a training folder. Therefore train underscore generator, which will take care of augmentation, pre-processing, everything. And the epochs, number of epochs that you are running, this is for 50 epochs you are running. So you can able to see the training accuracy. The training performance is good. The training accuracy we are getting almost close to 95% and the loss is also smaller loss value. Then once the model, once you are satisfied with the training, once you feel that the training accuracy is good, then you can stop training the model and then you can go for evaluating. You can test your model. So for testing the model you have to pass in the previous ANN when we have learnt, we were passing X test. So here you will pass the images which are stored in test folder. So where all images which are stored in the test folder are stored, it is stored in a variable called test underscore generator. Here is where you have the directory where test images are being passed. So no other operation is being done here. You can see that no data augmentation or nothing of that is being done for test images. So test underscore generator is passed as an parameter to evaluate your model. So what model, using which model you want to test? The model that you have built. Which model you have built? You have built a CNN1 model. So using this you are, and then evaluate will give you the accuracy as well as the loss. So when you print the accuracy, we are able to see that the test accuracy of this model is 93.595%. And this is how you build the model and then you will evaluate it. Now, if you look into this particular CNN model that we have built, the CNN model had 5 layers of convolution, and we had these many different filters, and this is the size of the kernel that we had. Now, for this model, for the epochs of 50, the test accuracy that we got was 93.95. Now, let us see a slight variation in the architecture. Now, the slight variation here is, rather than building a 5 different layers of convolution, we are building only 3 convolution. We are building only 3 layers, and with these 3 layers, rest all parameters we have fixed the same. The number of epochs, there we had got 93% accuracy, and here if you see, we have got 94. Does it mean that we have to reduce the number of layers, and by reducing the layers we are getting the accuracy more? Answer is no. For this data set, for this size of the data set, for this kind of an parameters that we have chosen, 3 layers was sufficient to give us the good accuracy. So, this is how you can change, you can look into the difference between the 2 CNNs that was built. So, the first CNN model that was built was 5 layers, the second CNN model that was built is just 3 layers. So, this is how you can increase, decrease, and then see how the performance is varying. So, let us move on to the next convolution. This is just one more example for the interest of learners. Here what we are doing, we are still retaining it to 3, and what was the accuracy with the 3 layers? We had got an accuracy of 94.7. Now, with the 3 layers, but now we are going to change the kernel. Instead of having a 3 cross 3 kernel, we are now changing the kernel size to 4 cross 4. And then rest all the parameters is the same as what is been discussed in the first CNN model that is built. The number of epochs are retained the same. For just by changing, by tweaking one parameter, we can able to say that there is an change in the accuracy. So, we cannot say that it is an overfitting just by looking at this, because the test training accuracy is also equally good. Training accuracy is good. So, we can say that the model is performing. So, change the number of convolution, increase the number of convolution, decrease the layers, change the number of kernels, change the size of the kernel, then add the dropout, without a dropout. These are the hyperparameters you will be keep changing, and then you will work on the models. This is how you build your own custom, you build your own convolution CNN model. Then we have something called as a transfer learning. This is also an important concept that has to be covered. We have an transfer learning. What exactly happens in transfer learning is the model that is trained on some other data, that particular weights or that particular model weights can be used to work on your data set. So, for example, when we take a winning architectures like VGG16, VGG19, ResNet, AlexNet, GoogleNet, these are all winning architectures. These architectures are built and these models have performed exceptionally well on ImageNet dataset. So, on this ImageNet dataset, these models have performed exceptionally well. Now, what we will do? We will take the weights of those models and we will use that weights to perform on our data set or on our problem statement. So, what we will do? So, we have to import, this is called transfer learning, we will import VGG16. So, we will import VGG16 from applications, from Keras applications. Then look at the way that we are writing a code here. Now, VGG16, 19, all these are the models which are worked on ImageNet, which was built on ImageNet dataset. ImageNet dataset is a color images. They are 3 channeled images. But what image that we have considered considered, the image that we have considered here is an grayscale image. That means it just accepts only one. But color images will have a totally 3 numbers, right? It will have 3 channels. So what we will do, we will concatenate, we will just to mimic that it is also a 3 channeled data set. So we will take our input image, which is of 128, 128, 1, and this entire we will give it to an variable input underscore tensor, and this is a single channel because it is a grayscale. But when we are using VGG16 transfer learning concept, it requires to work on 3 channels, because those models are built on color images, which is 3 channels. So we are now replicating, we are concatenating, we are writing input tensor, input tensor, input tensor. Why we are doing this? Just to make it as 3 channels. So concatenating, by doing this, now your image has you know, you are mimicking it as a 3 channel images. Yeah. So this entire is now assigned to this variable. So you will no more pass 128, 128, 1, but rather your input input now will be your RG. This is your input. Okay. Now look at how we will pass this transfer, how we will use this transfer learning. Now when we had built your CNN, the previous when we have seen the CNN model that you have built, we were writing convolution, ReLU, pooling, we were doing those layers, we were adding those layers. But now those layers are important for you to extract the features, but there is some model which is performing exceptionally good for extracting the features. That model here is VGG16. I will use that model to extract the features. So you see this part of a code. And before we look into this, the flatten layer we will write only at the output of that last convolution layer, flatten, then we are going to write a fully connected neural network. But nowhere we have written convolutional, ReLU, max pooling, we have not written that. Why do we require that? We require that to extract the features, but I do not want to use those layers to extract the features. There is a model VGG16 which is very good in extracting the features. So I will use that VGG16. This VGG16 worked well on what? This was trained on ImageNet data set. So the kernels which were used for that ImageNet data set, the values of that, the weights of that will be used for our Alzheimer's disease classification. So weights we are using. Now on what data it has to work? It has to work on our data, which is 128, 128, that is you are passing this as an input. Now those weights, I do not want it to train once again, I do not want to modify those, I want to use as it is. Therefore include underscore top, you are making it as a false. Therefore the meaning of this is those layers are not being trained once again. You are not training those layers, already it is well trained. So it is input include underscore top is false. This entire is given to VGG16. Now that VGG16 you will add in the sequential model, you are adding that VGG16. Before flatten, you are adding this VGG16, but this VGG16 you want it to work for your data, but you want to use those kernel values only. The kernel values which has worked exceptionally well on ImageNet, those weights I want to use to extract the features of my Alzheimer's disease. Therefore, you are nowhere writing CN convolution, max pooling, instead we are writing this VGG16. Why this VGG16? Because the variable name that you have passed here is this, that is being passed, then flatten layer, then rest everything is same as what you have seen it. So rest everything is same as your flattened layer. After flattened layer, you are adding fully connected neural network. Then the hidden layer, 4 output layer has 4 neurons. Activation function is softmax. Compiler. Then you are training the model. You are training this entire is given to a variable model VGG16. So using this model, you will compile. Using that model, you will train the architecture, train the model. So you will see that the accuracy is not that great, not necessarily that always when we go for transfer learning the accuracy should be good. Maybe for this particular data set, when we have used VGG16 model for this data, we are not getting that good accuracy. So this is how, this is what is a transfer learning. What is a transfer learning? This is also one of the important concept in CNN. It is all about extracting the features. What is helping you to extract the features? It is the kernel. Now the values inside that kernel randomly it will be choosing initially. Then during your back propagation time by reducing the loss, and then you will be keep changing those weights in the kernel. So instead of you doing this entire, somebody has already developed a very good model. So you want to take the those kernels to extract your features, to extract the features of your data set. Then this is your transfer learning concept. So this is all about the implementation of CNN. We will stop the class here. Thank you.